All right, so here is sort of some extra tidbit information about graphing rational functions. So our rational functions, because we're dividing and because of our division by zero rule, we can sometimes, as we've been working with these functions, we can sometimes simplify out some of our pieces. And so when we're graphing our original function, those pieces that we've simplified out don't necessarily go away. So let me give you a few examples and sort of show you what I mean by that. So we can sometimes have holes in rational functions. So if I'm taking a look here at this rational function, f of x is x squared plus 4x, if I want to find the holes here, I'm going to go ahead and factor my numerator. So here I'll get that f of x is equal, I'll pull out an x and I'm left with x plus 4, all over x plus 4. So I can see here, this is certainly a rational function, but when I factor my numerator, I can simplify out my entire denominator with a piece of my numerator, and I'm just left with f of x is equal to x, which is a linear function. But this piece here, this is not a linear function. So what happens is, whenever we can simplify out, we sort of end up with a hole there. So looking here, I know that my denominator, x cannot equal negative 4. So this is the piece that I simplified out. But when I'm looking at my simplified version of this, it doesn't look like I should have any restrictions at 4. So what we'll do is we'll go ahead and factor like I just did. And whatever we simplify out, we set that equal to 0, and that's where my hole happens. So looking here, this, you'll see this red line is the line y is equal to x, because my simplified version of this function was f of x is equal to x when I simplified out my x plus 4s. But what happens is at negative 4, I'm still undefined there. So what happens is we just end up having a hole in our graph. So let's take a look here. Let's find the holes in these rational functions. So for this one, I can go ahead and factor. So here, factors of 6 that add up to negative 5, we'll use 6 and 1. So negative 6 and positive 1. Factors of 3 that add up to negative 4, so negative 1 and negative 3. So it looks like here nothing actually factors out. Let's see, x minus 5, x plus 6. Yep, there may be a typo in this problem. Okay, let's move on to the next one. Ooh. So here I have x minus 2 in my denominator. Here I have x and x, factors of 4, so x minus 2 and x minus 2. So g of x, you ended up happening like I wanted you to for the purpose of this video. So x minus 2 and x minus 2 simplify out. So what I want to do is I want to take this here, I want to take this x minus 2, that's my piece that's simplified out, and I want to set it equal to 0. So when x is equal to 2, I will have a hole there. And what I need to do is I need to go ahead and plug 2 back into my simplified version of my equation, or of my function. So my simplified version is g of x is x minus 2, because this is all that's left here. When I plug this in, g of 2 is going to give me 2 minus 2, which is 0. So at g of 2 equals 0, so 2 comma 0, this will be a hole. So don't forget to go back and figure out what the y coordinate of the hole is. So h of x here, I can go ahead and factor out. Here, let's factor out a 4. And here I'm left with x plus 5 all over 2x plus 5. So h of x also worked out quite nicely. So here I can simplify out my x plus 5s, and my simplified version here is h of x is equal to 4 over 2, which is 2. So this function here will just be a line. So I know that my whole, I can take my simplified out piece, and I know that I will have a whole where x is equal to -5. So here, let's keep going. For my oblique asymptotes, I know in the very first video we said that if the degree of my numerator is larger than the degree of my denominator, that there is no horizontal asymptote, and that's not actually true. Well, I guess it is true. There is no horizontal asymptote, but there is an oblique asymptote. So oblique meaning there's a diagonal asymptote. So what we have to do here is we have to use long division to locate where the diagonal asymptote is. So I can go ahead and say that x minus 2, and going back to when we worked with polynomials, we can use long division. So here I'll have x, and I'll have x squared minus 2x. I can subtract, so this is going to give me 3 minus -2x, which gives me 5x. Bring down my positive 3. This will give me 5, so 5 times x minus 2 will give me 5x minus 10. And I can subtract. Here I'm left with 0. 3 minus -10 will just give me a remainder of 13. The remainder isn't necessarily what we're focused on. What we're focusing on here is my function piece. So my oblique asymptote will be at y is equal to x plus 5. So looking here, here is my x plus 5. You can see I also have my vertical asymptote at x is equal to 2. And if we were to factor, we may see that this maybe barely touches the x-axis there. We could plug in 0 for y or for x and get that y-intercept there. So if the degree of the numerator is larger than the degree of the denominator, it is correct in saying that there's no horizontal asymptote, but there is an oblique asymptote, and we need to use long division in order to find it.